So my name is Robert. I'm a staff software engineer at Decodable. I'm working there for a little bit over a year. And before Decodable, I've been working at a company called initially Artisans and then Ververica. It's the company that initially commercialized Apache Flink. And the company has been founded, and I'm one of the founders, by the original team that worked together at the Technical University of Berlin to build this stream processing framework that is now Apache Flink. So I have quite a lot of history with Flink. So I remember the early days, and I've worked on a lot of things over this 8-year period, from the various deployment integrations, Kafka integration, APIs. Also, I've spent a lot of time building up the open source community and evangelizing Apache Flink and helping the first companies to adopt it. And today I'm going to introduce Apache Flink to you, some of the core building blocks and underlying concepts. I've also been asked by the organizers of the meetup to talk a little bit about the community and ways to contribute to open source. And I will also do a short demo on how to get started with Flink. So if you have any questions, please unmute yourself and ask, and I will explain or give you an answer. So I will talk about these 4 areas: the, let's say, streaming foundations, state, time, and events. Then I will talk about the runtime. This is a pretty big topic. I've selected only one example topic that I will dive into. Then I will talk about integrations, connectors, and ways to deploy Flink. And finally, I will talk about the community a little bit and how to contribute to Flink. So from a very high level, what is Apache Flink? Flink is a data processing engine for low latency, high throughput stream processing. It's an open source project at the Apache Software Foundation, and it's one of the biggest projects there. So it often ranks high in terms of mailing list activity and a number of committers and contributors. And it enjoys really, really wide industry adoption. Companies like Netflix, Uber, Alibaba, Reddit, TikTok are all using Flink in production today. And besides that, there's also lots of cloud providers that are offering Flink. So AWS has an offering for Flink in the cloud. And I'm also working at a company, Decodable, which is offering Flink as a hosted service in the cloud. So let's look at one example use case of what you can do with Flink. In this example, we have 2 MySQL databases, and we want to join tables from these databases and build a record that we will ingest into Elasticsearch. So say you don't want to overload your MySQL server with search queries from your users, and instead you want to do the search more efficiently with Elasticsearch. Then you can use Flink to connect to these 2 databases and read all the data from these tables, and then read the transaction log of MySQL to also apply any update that is applied to the database into Elasticsearch. And we use this join operator to basically build full, let's say, documents in Elasticsearch with all the information you need. So let's say you have a table with users, and you have a table with items, and you want to attach the user that created an item. And with the join operator, you can embed the user information into each item, and then you can find all the information at once in Elasticsearch. And you can do this with Flink with fairly low latency. So that's one example of a real-time join and real-time index ingest using change data capture with Apache Flink. There's more use cases for Flink, so you can also use it for real-time reporting, where you have dashboards that are live updating as the input data is changing. You can use it for all kinds of sophisticated alerting use cases, where you want to build windows over time, or do some aggregations, counting, min-max, average, or machine learning for alerting. Then the use case I just described, real-time cross-database joins, machine learning, change data capture. There's all kinds of use cases that you can use Flink for. It's a general programming framework that you can use with Java or Scala. So you're really flexible in what you're doing with it. So let's look at the 4 areas that we're going to discuss today, and let's double click into the streaming foundations. So Flink offers 3 underlying primitives: events, state, and time. Events are represented in a data flow. So you basically define one or more data sources. You can define partitioning of data, and you aggregate the data, and you're syncing the data. So this is an example data flow. You can build arbitrary complex data flows with multiple sources, multiple aggregations or joins or filters or maps, and also multiple things. And Flink is taking care of efficiently executing this in parallel in the cluster. And this in parallel is important because it allows you to scale up as the amount of data that you want to process is increasing. So here, if you have the sample data flow of the data source, aggregation, and sync, and you're running this with a parallelism of 2 on 2 machines, and each machine in Flink is called a task manager, then Flink would distribute the workload, as you can see below, where the sources are running twice, and only the sync is running once because it has been configured to run once. And as you can imagine, we can just add more task managers, and by that distribute the workload on more machines, and thus improve the performance and reduce the latency. The second primitive is state. And state basically means some kind of data that each operator holds. In case of the data source, it is if you're reading from Kafka, it's the current offsets of all the partitions that the source is reading. In case of the aggregation, it's if you're counting by key, for example, it's just the current count per key. And for the sync, it can be like transaction information from the transactions that you're currently writing into Kafka. And the state can grow quite large. So in particular, in the middle, for this data aggregation operator, imagine that you have like 1 million keys, or I don't know, 100 million keys, and each key is 8 bytes. You quickly get into large data sizes if you have multiple such operators. But that's not a problem because Flink has a sophisticated system for handling very large state. Flink guarantees that state is durable, and it achieves that by doing periodic backups. We call it checkpoints to cheap storage. So let's say every 30 seconds, Flink is writing all the state of all the operators to S3. And if something goes wrong in Flink, we can download the latest state from S3 and continue the processing from there. Flink also guarantees exactly one semantics for state and connectors integrating with Flink state. And this is achieved by consistently restoring the state of all operators. And by that, records might be sent multiple times, but changes to the state are only applied exactly once. And by that, all the counts, all the output records, and so on are consistent with the number of records. State is stored in pluggable state backends. So there is a state backend where you can store state in memory, and then there's also a state backend that allows you to store the state efficiently on disk using the RocksDB key value store. And RocksDB is a default state backend, and it allows you to store really large amounts of state in Flink, because you're not bound by the available memory, you're only bound by the available disk that you have across all your task managers. Let's talk about the final primitive here, and that is time. Time is an important aspect in streaming systems because we are in a low latency environment or real-time environment with stream processing usually, but we also don't want to sacrifice correctness. Like, we want to have results that are consistent. And Flink handles time by making the underlying engine aware of the time of events. So imagine you have these JSON objects from some logged-in system. So you see the operation and you see a time field here. And you can basically tell Flink that in my stream of events, I have a time field. Please respect that time. So if you're using a windowing operator, so you want to collect the login events by time, and here we are building an hourly window. So we are building a window from 9 a.m. to 10 a.m., then the window from 10 a.m. to 11 a.m., and so on. And we want to collect this stream of events, which is arriving out of order, into these windows. And Flink can do that. So Flink will buffer the events in the window operator so that we can collect all the events that happened at between, let's say, 10 and 11 here. So the question is, when have we seen all the events that are arriving out of order for a certain window, so that we can say we can close the window and we can evaluate the content of the window. And this is done in Flink using a concept called watermarks. So every now and then, the sources in Flink will emit a special record that say, now the time has progressed to, let's say, 10, 11 a.m. And this means that the time has progressed past 10 a.m. So this window here can be triggered. We can analyze the data because we can be sure that no further records will arrive for this 9 to 10 a.m. window. So the watermark is like a virtual clock for event time. And this is a very powerful concept because it allows you to reprocess old data as if you would process it in real time. And you get consistent results. So even if you're processing data from 10 years ago, you are able to run the same windows with the same contents and get the same results as if you would process it in real time. And this is basically giving you correctness over real-time streams at the cost of latency. Because as you see here, we are buffering records. So this naturally increases the latency until we see these records. But that's something that you can configure as a user of the streaming system, whether you want correctness or low latency. So how do you get access to all these features that I just described? Or let's say not features, but these underlying primitives of a streaming system. And there's various APIs available in Flink that are on a spectrum from expressiveness, like really low level APIs, and ease of use. And for the really low level APIs, in Java, we have something called a process function that gives you raw access to the events, to the state, and to event time. So you can compose an arbitrary DAG of data in this low-level API and build your own join operators or windowing operators. If you don't want to build your own windowing operators, you can use the DataStream API, which offers abstractions for windowing and aggregations and so on. If you don't want to write Java, you can either use PyFlink or Flink SQL. So there's gone a lot of effort in the Flink community into developing Flink SQL. And it's a really, really nice, powerful API that allows you to express complex streaming applications with a few lines of SQL code. So it's pretty impressive what you can do with a little bit of SQL strings, and it will turn into complex streaming applications that are pretty efficient because we can apply a number of optimizations. So let's look at a Flink SQL example. On the left-hand side, you're seeing the statement to create a table. So you're basically defining the schema, and here you're also defining a timestamp field, which you can use for doing event time processing. And then we're defining some properties that are used for the Kafka connector, so that we can connect to the Kafka host. And on the right-hand side, we are defining a tumbling window. So basically what I just showed in the streaming section, you can also see here on the right-hand side. So we are basically collecting data for 1 hour based on the timestamp field, and then emitting the count of elements for each window downstream. And that's all you need to build a basic tumbling window in Flink SQL. Now let's go to the other side of the spectrum and look at the low-level API in Flink. And this is called the process function. And this process element function gets called on every input element that you're receiving from your data stream. And then you see that in this context object that you're also getting, you can access the timestamp, like the event time of that record. You can write to the state. You can also read to the state. And you can register timers and evaluate stuff on these timers. And the context is also giving you access to watermarks. So this is a very low-level API, but it allows you to build custom operations. And what I have seen from Flink users is that they are using this process function to build custom join implementations. Imagine that you want to join data that goes back like multiple years, and you want to keep the state of, let's say, the last month in Flink, but for the long tail, you want to do a lookup in the database. This is fairly simple to implement in a process function, but it's not something that you can do easily in Flink SQL. So now let's talk about the runtime of Flink. And I'm going to discuss one topic here, and that is how we do checkpoints for exactly once in Flink. So as I mentioned, Flink has stateful operators, and we are periodically taking a snapshot of the state to allow going back in case of a system failure. And the naive approach of doing these checkpoints would be to stop processing all the data, back up the state of all operators, and then continue the processing. The downside of this approach is that you're interrupting the processing, which causes high latency, and it also causes poor resource utilization because you need to drain the pipeline first. What Flink is doing instead is that these checkpoints are done while we are still processing the data. So they are done in line. And for that, there's a central component in Flink called the checkpoint coordinator, which is triggering a checkpoint at the sources. So both sources will receive a message that it's now time to create a checkpoint. The sources will then back up the current state. So let's say it's Kafka sources. They will write their current offsets into S3, and then they will emit barriers downstream. So these are special messages that they're sending downstream. And these messages tell downstream operators that at this message, they have to write their state into S3. And for this aggregation operator, it will basically wait until the barriers from both sources have arrived at the operator. Once the barriers have arrived, we will write the state to the state storage. And then this aggregation operator again is sending downstream these barriers, and then the sink will also write its state. And once that has happened, we have all the state of all the operators written to S3 in a consistent way. So if there's a failure in Flink, we can download this last completed checkpoint and restore from that and continue the processing from there. And what is important to note is that this checkpoint is consistent, because events are not allowed to overtake these barriers. And this has the effect that it's like a consistent snapshot. Like it's like we are stopping the entire pipeline and took a backup of all the operators at the same time without stopping all the operators. And let's say we are the input messages from Kafka have a certain offset, and if we lose the machine and we need to recover, we will continue at the specific offset, and we will reset all the counters, we will reset all the aggregations, we will reset all the window contents to the state of this offset. And this is how we achieve exactly one semantics, because we reset the state consistently across all operators. And this has a lot of optimizations in practice. So there's options to make these checkpoints. There's various configuration options to make this really efficient. But that's the underlying algorithm that Flink provides. Now let's talk about integrations and connectors in Flink. So this is the slide where I can put all the logos. And this is just a selection of the systems that Flink can connect to. And that's actually also, so let's first talk about the connector. So I think the most popular connector is Apache Kafka, which allows you to do exactly once reading and writing from and to Kafka into Flink. We also support Pulsar, Amazon S3, like we can monitor S3, whether there are changes on files and then ingest these changes into Flink. We can also write to Flink, and we can read and write from Amazon Kinesis with support for Elasticsearch. And here at the bottom, I've put some databases because there's a project called Flink CDC connectors, which allow you to do change data capture, as I shown in the beginning, with SQL databases. So you can use Flink SQL, for example, to join tables from different SQL databases inside Flink. Then Flink supports a number of data formats, such as the Debezium format, Afro, Parquet, ORC, and we have a bunch of observability, like metrics integrations for observability. Now let's talk about the ways to deploy Flink in your cluster or on your hardware. And there's lots of options, and this decision tree might be a little bit overloading, but I'll walk you through that. So there's different resource providers. There's Kubernetes, and that's, I think, the most popular these days. There's the option to deploy on Docker. You can do it yourself, like just starting JVMs and bash scripts. And we also still support Hadoop Yarn, but that's not really popular anymore. So let's focus on Kubernetes. For Kubernetes, you can directly talk to Kubernetes, apply the resources, and start JVMs for Flink. Or you go through the Kubernetes operator, which Flink is also providing as an open source project. And the operator allows you to use the native Kubernetes mode and the standalone Kubernetes mode. In the native mode, Flink the operator will deploy the job manager, and the job manager will talk to Kubernetes to allocate or deallocate pods for the task managers. So the job manager is the central coordinator in Flink, and the task managers are the workers in Flink. And the native Kubernetes mode is interesting if you have changing workloads. So if you submit jobs and let's say it's batch jobs and they finish after some time, or you have streaming jobs that only run for a certain amount of time. Because in the native Kubernetes mode, Flink will allocate as many task managers as it needs to process your workload. And once it's done with the processing, it will deallocate these task managers again. In a standalone Kubernetes mode, you define upfront how many task managers you want, and then Flink will allocate them and do the processing on them. My personal recommendation, and that's also indicated by this dark green line, is to use the Kubernetes operator with standalone mode and an exclusive cluster. We call it application mode. That's my recommendation for deploying Flink. But there's lots of options, and it might look overwhelming, but if you're checking out documentation, it's quite doable, and it's a good experience to deploy Flink. So finally, let's talk about the Flink community. So first of all, Flink is part of the Apache Software Foundation. And one of the mottos in Apache is community over code. So the ASF puts a lot of weight into community, and community is more important than just the code of the project. There's lots of principles and best practices that the ASF has established over the, I think they're 25 years old or so, where they have established processes and best practices how to run a successful open source community. And the sheer number and the success of these projects proves the ASF right that they know a thing or two how to build open source communities. So the ASF is extensively using mailing lists for communication, and basically every project is following the same pattern. So does Flink. There is a mailing list called the dev mailing list, where contributors and developers are discussing the development of Flink, new features, releases, and everything that is needed to manage the project. There's also a user mailing list where people can ask questions and the developers will answer them with the user. There's another mailing list called the private mailing list that is for the project management committee of Flink to discuss matters like adding committers or adding PMC members or reporting to the Apache Software Foundation board. Like a year or so ago, the Flink community also added a Slack instance that is mostly used for user support. And then there's quite a lot of information about Flink on Stack Overflow, and also in the Apache Jira that we're using for bug tracking and also tracking of feature progression, which is quite helpful for seeing when something has been fixed in Flink or which versions are affected by a certain bug, or for workarounds and so on. And then there's meetups and conferences where the community is meeting. There's a conference called Flink Forward. Also at the current conference organized by Confluent, there are quite a bit of Flink talks by now, also at the Kafka Summit, and other global conferences. And finally, there's people on Twitter that you can meet that are from the Flink community. So let's talk about releases in Flink. And the releases are managed by release managers, which are taking care of tracking the progress of all the features that go into a release, and also the stability, whether there are any blocking issues that would block the release. And they will also organize a vote. So the Apache Software Foundation has a rigorous process for creating releases. Basically, the release managers propose a release candidate, and then there is a 3-day voting period where other PMC members validate the release, check whether it's working, whether it's it's done the due diligence on license files and all that stuff. And then usually a release takes like multiple rounds of votes until it's accepted. And once it's accepted, we put it out in the public. Flink is currently releasing 2 to 4 releases per year, but also multiple smaller bug fix releases in between. So the current Flink release is 1.17. The next one is 1.18. I think the feature freeze is pretty soon. As part of the feature development and release process in Flink, we are using a process called FLIPS, Flink Improvement Proposals, for discussing major improvements to Flink. So when you're working on a big feature, let's say you're implementing autoscaling in Flink, you're adding a state backend in Flink, you're adding new SQL syntax, you write a flip in our wiki where you discuss like a design document basically of the feature. Then you propose this design document on the dev mailing list, where you get feedback by the community and questions by the community to make sure that your flip is a good fit for Flink. And once your flip has been voted and approved, you can start working on it and open pull requests on it. And finally, I would also like to talk about contributing to Flink. There's a pretty extensive guide on our website for how to contribute, not just code, also documentation and user support and so on. So at a very high level, what is important to remember to contribute to Flink is that you should first reach out via Jira or the dev mailing list or Slack if your contribution makes sense and if people are willing to review it. Because often there's quite a lot of knowledge in Flink that something is very difficult to fix or has been tried before, or it's not a good fit or whatever. So we want to avoid that people are working on a feature and then it doesn't make it into Flink. That's why it's better to first ask and then open your pull request. And then contributions don't have to be code all the time. Reviewing other people's pull requests, writing documentation, and user support are also very, very helpful contributions to the community. And also, we often see this, that people do contributions for the sake of just contributing or internet fame or like CV optimization, and often these pull requests get rejected. So only contribute if you found a bug or if you miss a feature or if you need something yourself. So that's all I want to say about the community. Now I want to also quickly talk about steps how to get started with Flink. And I would recommend, in particular if you're a Java developer or if you're a developer, to first look into how to write a Flink job. So you can do that using Flink's Java API or Scala API, or you can do that using Flink SQL. Then look into how to deploy Flink locally, and finally look into how to deploy Flink on a cluster. And I am going to demo now quickly an example Java API program that I will show you how to deploy this example program on a cluster. And I will show you how to deploy a Flink cluster and then show how to submit this job that we've implemented on this cluster. So let me switch my screen share to my main screen. So I have implemented a basic Flink job, which is doing change data capture against MySQL. So I assume you can see my IntelliJ and my code. And we have here a main method. And in this main method, we get a stream execution environment. And the stream execution environment allows you to define sources. So you can do environment.add_source for reading from various data sources. Once you're reading from a data source, you get a DataStream object. On a DataStream object, you can do things like flat map, which is just doing like tuple at a time operations. Keying, you can use a process function that I've talked about, the map function, the print operator, which is just writing the contents of the stream to standard out. You can define sync operators to write data to sinks. You can connect streams, you can do windows, filters, and all of that stuff, joining. So all these operations are available to you to work with your real-time stream. So let me quickly define, just for the sake of example, let's say we want to transform a stream of CDC data into integers. I don't know, it doesn't really make sense. So this is how you would do tuple at a time transformation. So you get a call to this map function for every input, and then emit the length of the stream. And then we can also do instant print to get the output of the stream. So now, and okay, I also should mention what this source here is doing, this MySQL source. So this is a change data capture source, which means it's connecting to a MySQL database and then reading all the data in this table. And it's emitting Debezium formatted records, which are change events in JSON that we can then process. So let me compile this Flink job with Maven. I need to format the code properly with Spotless. And while the code is compiling, I will, so now the compile is done. So now I will start a Flink cluster. And here I have downloaded Flink 1.16.1 from the Flink website, unzipped it, and this is what you find in the Flink directory. So there's fairly standard stuff like a bin directory with the scripts, configuration directory, lib directory with the jar files, and that's basically it. So I will use the bin start cluster script to start a Flink cluster. Once that is done, sorry, I just need to find the Chrome window. I can access the Flink UI on localhost 8081. So you're now seeing it's an empty cluster, no running jobs. There's one task slot available. So in fact, go to the task managers. You can see there's one task manager connected that is not doing anything right now. So now let me submit my CDC job. And for that, I will use this Flink binary here with the run command, where I'm passing the class with the main method, and then the jar location, and finally some arguments. So I will want to read the employee database with the employees table, and my SQL username is root, and my password is password. So these are the arguments I'm passing, and then I'm passing this here with this parameter tool, and I'm passing them into the MySQL source. And this is, by the way, this employees table that I'm reading, which is like first name, last name, gender. It's a standard MySQL example. Okay, so I will submit this job now by running this tool. We can ignore these warnings. So now it says job has been submitted. If I now open the Flink UI, we'll see that there's a job running since 8 seconds. And if I open this, you're also seeing like there's a source operator, there's a print, then there's a map function that we've defined, and there's another print. And we can see that we have processed 80 megabytes of data, 150 megabytes of data, so it's still streaming. 181,000 records. Yeah. So now this is running. We can also see here on the task manager that it has a little bit more memory allocated for the different tasks. So now let's look at the output of this Flink job. It will be just in the log directory. And this is the task manager output. So we see here, these are the counts, or these are the string slices from this one output. And these are the MySQL CDC events. So we see employee number, birth date, first name, last name, and so on. So if I follow this file, and I'm now going to make a change in the source table, we should see a change here in this output file in real time. So if I'm renaming then here Georgie to Georgie++, and I commit this, then boom, you see here's an update. So now first name has been updated. And this is happening basically in real time, right? So if I click the button here, you see the change here. And you also see this updated length of the string. So this is real-time change data capture with Flink. We are following the bin log of Flink and ingesting these changes in real time. And you can then write it here to file, or you write it to Elasticsearch or another database, or whatever you want to do with it here in your Java code. And that's all for my demo. Now I'm happy to take your questions.
Hello, this is Amal from Ericsson. So I have a use case for which I would require some clarification on how to handle that use case, or if there is something inbuilt in Flink to handle the use case.
Mm-hmm.
Suppose I want to process few files and store them as external tables on top of Spark, and say I want to do it as micro batches, say per minute I want to process it. So which means in a day you would have about 1,400 odd files in your Spark external tables. Mm-hmm. So these small files are left as it is under the Spark external tables, or we require them to do a consolidation on top of it, or does Flink provide any mechanism that it auto aggregates the files at the end of the day?
Okay, so first of all, you can use the file system sync in Flink to file system sync, which allows you to write data so you can basically define a rolling interval, how often you want to write the files to the downstream system. So for your question regarding exactly, I think it's here the rolling policy that you want.
Yeah.
Where you define this. So Flink does not, this source does not support merging the files at the end of the day. But what you can do, of course, is you can just write daily buckets instead of buckets by minute.
Okay.
And also the question is why do you want to use Spark for the processing? Because you're basically introducing latency. So if you're doing like minute by minute buckets, you're introducing latency into your whole pipeline and complexity because you have Flink and Spark in your pipeline. I would like to understand what are you doing in Spark, because maybe you can do this right away in a real-time fashion with Flink.
Okay. Spark we're using for storing it for processing, basically for pulling reports out of the external tables. So we write Spark SQL on top of the external tables where we store our data. So mainly it is used for integrating with the external reporting tools like SAP BO or Tableau or those kind of tools.
So the question is,
for persistence, we use like a distributed file system, but Spark is mainly used for the SQL structure that it gives.
So Flink has also SQL support. So you can use Flink SQL also with real-time streaming to do these. So you could also build these reports in a real-time fashion in Flink. So let's say you're aggregating over the, items purchased per region. And whenever there's a purchase, Flink would update the downstream report in real time. So that it's just like food for thought to make this faster.
And sorry, I have another question. So this in this case, so suppose if I want to remove duplicate records across hours, let's say in a span of 6 hours, is there a mechanism to do that in Flink? Or like say I want to remove duplicates across hours, like I get record A at the first hour, and if I get the same record at the 6th hour, I do not want that record which I get in the 6th hour because it's the duplicate of the record which I got in the first hour.
Yeah, so Flink SQL provides syntax for deduplicating, as you can see on my screen. And also in Flink Java, you can implement a deduplication operator. So this is possible, yes.
Okay. Yeah, thank you.
Cool.
We have
yes, we have questions in the chat. So how is it different from Apache Spark? What are ideal use cases where Flink is the way to go? So Apache Spark is mostly a batch processing framework, and Flink is mostly a stream processing framework. I think that's the main difference. Yes, Spark has also Spark streaming. And I don't know like what the feature set is today, but last time I checked, Spark streaming has some basic Flink streaming stuff, but Flink is much more sophisticated. So Flink has like much more libraries on top of stream processing, much more connector support. It can handle very large state, very fast checkpoints, very low latency. And Spark streaming, for example, is using this micro batching approach, where it basically uses the batch engine for stream processing. So it's collecting data for some time, then submitting the data to batch engine, and then emitting the output. And from the outside, this looks like a streaming system, but in reality, this is introducing latency and complexity and load on your infrastructure. So Flink is the ideal system for everything that is real-time, low latency, high throughput stream processing. The next question is, could you outline how Flink compares against other streaming options? So yeah, I think I just spoke about Spark streaming, which is not seeing, I think, a wide industry adoption from my knowledge. Kafka Streams, I think, is the other stream processing framework that also enjoys popularity. Kafka Streams is tightly integrated into Kafka. So you need to deploy Kafka if you want to use Kafka Streams. Flink is completely independent of Kafka. You can read from Kinesis or from any other, or Pulsar or any other streaming system. You don't need to have Kafka. Kafka Streams is also relying on Kafka to exchange data between operators. So if you look at this Flink job here, in Kafka Streams, this connection here and this connection here and this, like these three connections that send data between these operators, they would use Kafka in between. So the amount of I/O that you're putting into your Kafka cluster is really, really high with Kafka Streams. And also state updates are written into Kafka and Kafka Streams. So yeah, if you have Kafka anyways, and you have like a not very demanding use case, and you want to just integrate it with your existing application deployment framework, then maybe Kafka Streams is an option. But if you have a heavy workload and you don't have Kafka, or you don't want to overload your Kafka cluster, then I think Flink is the better option. Then there's another question. How does Flink address the problem of out-of-order streams, late messages? It's a very good question, and I think I didn't cover this earlier when I talked about the windowing. So the problem is the following. I talked about event time and watermarks, and that this virtual clock is progressing the time. So what happens if we close the 9 a.m. window and then there's an out of order or late event that should still go into this 9 a.m. window? So in Flink, there's in the windowing API, windowing API, there's something called allowed lateness. This is basically telling Flink to keep the window around for some more time. So if you know that records might be late for up to 5 minutes, you can define an allowed lateness of 5 minutes. And this means that Flink will close the window, but keep the window around in case later events arrive, and then we'll reevaluate the window for late events. Then there's also a way to define a side output for late data. So this is a special output of the window. In case a late event arrives, this event will be sent to the special stream, and then you can give this data special treatment. Like you can, let's say you're aggregating into a database, you can manually update the aggregate by manually writing an update into the, like do a, I don't know, like SQL update statement to handle this late data. And this is how, and then of course you can use the process function and do arbitrary code to handle late events. Okay, are there any other questions?
Hey Robert, this is Maharajan. So I do have a use case similar to which you kind of demoed, using a CDC from MySQL to another sync operator, but I've been trying to use Kafka on Azure using the event hubs. But I just found out that I think is MySQL much simpler or on a very low memory intensive operation? And is there any managed Flink service on Azure?
I don't know if there's a managed Flink service on Azure. I don't think so.
Okay.
And these CDC connectors in Flink are fairly low resource consumption. So you can run this with a fairly small resource footprint. It depends a little bit on your data that you're streaming. So if you have very large records, then you might need a little bit more heap to allocate these objects. But in general, it's so the thing with all the CDC is that MySQL is always single instance. Like, yes, you might have replicas that are following your bin log, but there's only one master that is writing to the mid-log. So there's only one Flink instance or usually one Flink instance is sufficient to read the bin log, because there's anyways only, it's not parallelizing this process.
Okay. So the way it's going to be deployed is the Flink is going to connect it through the DataStream connector. Does it have a direct MySQL connector?
Yes. So there is this Flink CDC connectors project, and there's the overview of all the connectors, and here is the MySQL CDC connector. So it shows you how to add the dependency and how to create, like in SQL and also in Java, how to connect to MySQL.
Okay, so I think our single Flink instance is enough to do all the connections, unlike Kafka, where you need to have a Kafka Connect work cluster and then DBCM on top of that. So that kind of complicated.
No, exactly. This is the big benefit of Flink, that you can run everything inside a single Flink job. Yes.
Okay, so one Flink instance for one particular DB is enough to have enough parallelism, right?
Yeah, so you only need a single instance of the CDC connector anyways, even if you're reading multiple tables from the MySQL database. But then it depends on the kind of processing that you're doing. If you're doing a complex join, you might need more than one Flink task manager. But if you're just ingesting the data to, I don't know, Elasticsearch or to another, whatever, Kafka or so, then you only need a single Flink task manager.
Okay. Because right now the workload is simple, you're just taking data from one place to another. And that's all. So even processing might be to add a timestamp to the source data. So I think for that one instance might be enough.
Yeah.
That's great. Thank you.
Yeah, you're welcome. So in the chat, there's a question about design patterns for Flink. There's no specific, like Flink specific design patterns. You can use all the regular streaming patterns, like lookup joins, real-time joins, and all of that with Flink. Then there's a question about recovery. Does the whole deck start from the previous checkpoint whenever a task or pod or a node goes down? Yes. Yes, the answer is yes. So we basically restart the entire Flink job. Flink has a configuration flag called local recovery, which will reuse the local state. So if you have 10 task managers and one task manager is failing, then only this one task manager will need to re-download the state from S3. The other task managers will reuse the state that is local on their disk. So this is fairly optimized in Flink and can happen quite quickly, such a recovery.
But I'm continuing that question. So doesn't that mean that, one of the intermediate tasks is actually going backwards because it is starting from the previous stored checkpoint, right? Whereas a downstream task could be because it's using the local checkpoint, it may be ahead.
But the checkpoints are done. The checkpoints are consistent. So all the state of all the operators will be reset to the latest checkpoint. So there's the state will go back, but it will go back consistently for all the operators.
Okay.
But so if you use a sync that does not support exactly once, you will see duplicate outputs being written. So let's say you're implementing a custom function that is just writing data to MySQL without using any transactions, then yes, you will see duplicates in MySQL. But if you're integrating MySQL transactions with Flink checkpoints, then you can make sure that you're only committing the transaction on a successful checkpoint, which means that if Flink fails, we will abort the transaction, and then you won't have duplicates. So for every sync in Flink, you need to integrate with the checkpointing mechanism. So for the Kafka thing, for example, we're integrating with Kafka exactly once. For the file system sync, we have an implementation that is using this truncate call that is available in S3 and HDFS to discard data that has not been successfully written as part of a checkpoint. So many things in Flink also support writing data in an exactly once fashion.
So the situation arises in the context of one of the jobs we are looking at. So there we are actually aggregating events data over a period of 90 days. And the state is expected to run into few MBs for each cluster, as in you can think of it as an identifier. So now so in case the pod goes down, so I think the assumption. So is it okay? If the state for a single can run into few MBs, or should we look at partitioning it to make it much lighter?
No, it's not a problem to have multiple megabytes of state. So at Decodable, we have customers that have hundreds of gigabytes of state in a cluster.
I see. And the fault tolerance is achieved through checkpointing. So I think even if at any point of time it fails, you actually read that entire state, that state object back from the S3 or equivalent.
Exactly, like S3 or HFS. So let's say you're writing your state, I don't know, if you have small state, like a few gigabytes, you write it every 10 seconds. If you have large state, you maybe write it once a minute. And then in case of a failure, we re-download the state, reset everything, and then start from this checkpoint again.
Got it. Okay. Thank you.
You're welcome. There's a question in the chat. Are there options available to debug issues in Flink jobs and identify bottlenecks in the Flink code? Yes. So one option is I showed you my IntelliJ and with the Flink code, and you can really use your IntelliJ debugger to go through the code and check if it's doing what it's supposed to do. And for performance bottlenecks in the Flink UI, we have various tools. So we can actually do some profiling and build what is it called again? Sorry. A flame graph. Exactly. We can build a flame graph. And also we have back pressure monitoring, which is an important thing in Flink. And there's also metrics for checkpointing times and where the checkpoint gets delayed. And there's also all other kinds of metrics for the state backend and so on. So there's a lot of options in Flink to monitor bottlenecks. For benchmarking custom code, there's no infrastructure provided in Flink, but it's fairly easy to build something yourself. Like you just implement a Flink job, deploy it, and then measure throughput and latency.
I assume there is Kerberos support for Flink, is it?
Sorry, can you repeat?
Kerberos support and security.
Yes, there is.
And we should be able to run Flink jobs on Yarn?
Yes.
Yarn cluster.
Yes. Okay. If there are no further questions, then thank you again for joining. It was really good questions. I really enjoyed it. And if you have any questions, reach out to me on LinkedIn, connect with me on LinkedIn, connect with me on Twitter, follow me on Twitter. I'm happy to answer any question you have about Flink or stream processing or decodable. So just reach out. Thank you.